Hello everyone, welcome to my presentation. This is Professor Pan Zhou from Huazhong University of Science and Technology. And this is a joint work with other two researchers. One is from the Beijing Institute of Technology, another one is from the Israeli Institute of Technology. As we know, the graph data is ubiquitous, and learning with graph data is an important task. And for the graph neural networks, and usually we call for the short for the GNN. They have two basic operations. One is called aggregate, and another called combine. The GNN can complete the load classification task and the graph classification task. For the attack to GNNs, in the existing work, they mainly focus on the white box attack and the gray box attack, which is less practical threat model. And in this paper, we focus on the stringent and the practical setting. That is black box attacks to GNN with structural perturbation. And the challenges in these settings, we have three folds. The first one is we have very limited logits, and we can only launch the queries to GNN. And we have no exact gradient information because we are black box model. And the structure perturbation is an NP hard problem, and also it's quite hard for us to solve. And our contribution is the first, our work is the first work for the structure-based black box attack to GNNs. And we put the first sublinear regret bound for the bandit-based approach, and which is shown in this slide. And our attack is proved to be both effective and efficient. And for the threat model, we assume the attacker only knows the GNS model's prediction via query, and they can manipulate different edges, and the goal is to fool a targeted GNN. And for the problem formulation, we have the adjacent vector AV, and we have loss on each of the nodes, and we have the perturbation cost, and we formulate this problem as as an optimization constrained optimization problem, and we have the budget, the cost constraints, and we have the CW loss on each of the nodes. And this problem is NP hard problems. So what we can do is we only can launch the queries and make the loss function LSVT available to estimate the gradient. And simultaneously, we fit our black box model to the GNNs. And to solve the problem, we need to use the some bandit logic about the multi-bandits, and it's a sequential decision problem. We have the rewards with bandit feedback. We want to regret define as the combination loss minus the optimal loss only known in the hidden set. We want the time average of the regret to be approached to 0 when the time approach infinity. And so our attack can be regarded as an OCO, online convex optimization with bandit feedback. So how to choose the next line based on the bandit feedback is our main goal, and why we use the OCO in the non-convex setting. And we want to derive the closed form solution in the non-convex setting, and what we want to do is we need to estimate the gradient descent to find the optimal solution. And the challenge is we don't have the exact gradient when choosing the arms. So our solution is we want to estimate the gradient by the one-point gradient estimation from the bandit theory. And this is our attack, and we can relax the perturbation vector to be the continuous domain and relax arm, and we use the NEMA 3 to estimate the gradient. And we show our attack the demonstration. The first one, we relax the integer domain to the continuous domain, and we have the bandit updates, we have the rounding, and then we do the edge and node perturbation, and then we complete our attack. And this shows the algorithms, and we randomly choose the vector and perturbation, the vectors, and we launch the query, and we use the bandit projected gradient descent update to estimate the gradient. And then based on this, we can prove the theorem 1. This is our main results, and we can also show the our attack is dimensional efficient and compared to the zone algorithm, which is the linear one, and it's a SOTA in this area. And we will compare our method with the Zhu attack, reinforcement learning based attack, and random attack, and this is our data set. And these are parameters, and we show that our result is larger, the attack success rate is larger than 80%, but the second best is only the 80% at the most. And we also show that for the larger the successful rate, as the T increase, and reinforcement learning based approach requires 1.5 to 3 times queries, and our attack can achieve 10% to 20% higher than reinforcement learning. And we also observed that the larger successful rate as the cost increase and the attack successful rate cannot be improved for limited cost. And this is our conclusion. We are the first work to propose the structural perturbation-based black box attack to GN, and we have the sublinear gray bound. We conduct extensive experiments to demonstrate our attack. And this is our full version of the paper, and this is the code. So thanks for your listening.